So let's talk about power in an electrical circuit and fuses and what they are used for. From a while back, we know that power is energy per time or work per time. It is measured in watts, and we know that a watt is a joule per second. Okay. In talking about power, we're going to talk about energy as well. So let's take a look at, we have two ratings here. We have 2 watts used for a day or 100 watts used for a minute. Because what actually sort of is useful to us, or what we pay for in our electric bill, is the energy. So 2 watts for a day, how many joules would that be? So we can start with our given information. We know we have 2 joules per second. We know that we have 60 seconds per 1 minute, 60 minutes per hour, and what are we talking about? 24 hours per day. So if we go ahead and multiply that all out, we would end up with something like 172,800 joules. Okay, so we're just looking at how much energy consumption this would turn into. 100 watts being used for a minute, we do the same thing where we have 100 joules per second, that's a watt, and it's per minute, so we can say that 60 seconds is 1 minute. Seconds cancel out, and we're left with joules per minute, which is what we're looking for, and our answer would be 6,000 joules. And a joule is actually a very small unit of measure, so you see kJ very frequently. So this would be kilojoules. Let's get some space. So we would see kilojoules very frequently. That would be 6 of them. Okay, so let's take a look at the units. This is frequently helpful if I'm sort of having difficulty maybe understanding the relationship between quantities. I think about the units, and frequently that helps. So, units, we know that a volt, so the voltage, the potential, that's like the push on the charge. So it's how much energy is given to a certain amount of charge. A joule per coulomb is a volt. Alright, and when we talk about current, so when we talk about current, we're talking about charge per time. And we could look at, the units, so this would be amps. And an amp is a coulomb per second. Okay. So if we look down here at our formula relating, we know that power is current times voltage. Or, well, maybe we're just learning that. Power is current times voltage. So let's see. We have a, we have a coulomb per second. So current, an amp is a coulomb per second. Coulomb per second. So I'm going to box these in because this is what we're talking about. And when we talk about voltage, that is a joule per coulomb. And if we look at what happens with these units, it looks like the coulombs cancel, leaving us with joule per second, which, hey, that is a watt, which is measurements of power or units of power. So this is kind of proving to us that power is equal to current times voltage, or at least that the units work out. So we know that a joule per second is a watt. Okay, so bottom line, who knows? No, kidding. Power is equal to current times voltage, and the units work out. Alright. There are 2 variations to this formula. Power equals current times voltage. And I like to memorize as little as possible, so know this. And Ohm's law from previously we know. So you can basically just substitute in. You know, you could say V over R equals I, and then you would replace I with V over R, and you'd end up with this. And you could do the same where you solve for R and replace it. So we have two variations for the formula for power, I squared times R and V squared over R. But these are all you have to know. Okay, so at some point you'll be paying for your own electric bill, and it gets, well, here's the cost of electricity in Mammoth. I just looked it up. 15.98 cents per kilowatt hour. So what on earth does that mean? It's the energy that you pay for. And energy is in joules, but joules is a very small amount. So look at what happens. If we take, we know that a watt is a joule per second, so let's take 1,000 of them. Alright, so 1,000 watts, a joule per second. And if we multiply that by an entire hour, so 3,600 seconds, we see that the seconds cancel, leaving us with, and this would be 3.6 times 10 to the 6th joules. So this is what we describe as 1 kilowatt hour. Let's write that. That's important. Kilowatt hour. So basically a kilowatt hour is just a larger conversion for joules. Just like when you talk about the distance from here to Bishop, you don't talk about it in centimeters, you talk about it in miles. And so when you're paying for electricity, this is how much you're going to pay. And that was just some random source on the internet. It could be totally different. But this is, you know, ballpark. It would be something like that. Alright, so I think on our next page we have an example of that. Yeah. So, here is an example. We'll hide that for now. So an electric heater, and in general, I'll write this. Electric heat is what costs the money or uses a lot of electricity. If you're using electricity to run your stereo to produce sound or a light to produce light, it's not nearly as much as when you're using electricity to heat something up. So, you know, a stove or a microwave or a heater. So electric heater draws a steady 15 amps. This is a lot, okay? Extension cords are sometimes not rated to this and they would melt on a 120 volt line. So this is our typical wall socket here in America. How much power does it require and how much does it cost per month if it operates 3 hours per day and the electric company charges 9.2? Aha, the price has gone down, cents per kilowatt hour. So pretend we're getting some cheap electricity. We run our heater for 3 hours a day. That's kind of reasonable, right, in winter. So what do? Well, we know that for the power, so we know power is current times voltage, and we can just multiply. So we have 15 amps, 120 volts, and we get an 1800 watt heater. This is a big heater. A little one that you'd put at your feet, you know, might be like 500 to 1,000 watts. So this would be a big boy, right? It's cold inside. It's winter. So what about the cost per month? Cost per month. So what we're looking for is we're going to do that unit conversion stuff. And we're looking for cents over months. So we start with the information we have, which is this. This is the power draw of the heater. I'll zoom in for a little more space. So 1800 watts, and again I'm going to describe the watt in terms of a joule per second. So we know that our heater uses 1800 joules per second. We know that there are, so seconds down below, we put seconds up top, 60 seconds in 1 minute. And we know there are 60 minutes, that's a 60 minutes in 1 hour. And we know that we run the heater 3 hours per day. Notice how this is different, right? Normally we're just throwing in 24 hours per day because it's related to something else. But here, we only run the heater 3 hours a day. And then we have days, so 30 days. The question actually said that. 30 days per 1 month. Okay, we have months now in the bottom, which is what we want, but we want cents up top, or dollars. We want cost. So the other information we know is this, 9.2 cents per kilowatt hour. So we're going to go from joules to kilowatt hours to cents. So 1 joule, no, what was it, 3.6 times 10 to the 6th joules was 1 kilowatt hour. And prices have gone down. 1 kilowatt hour cost 9.2 cents. Whew, almost ran out of space. Okay, so if we multiply, you might want to try that. Multiply, divide, I think we end up with something like, it's going to say 1490.4, and this is cents per month. I'm going to abbreviate month as an M. So about $14. Oops, I mean about $15. And that's kind of reasonable, you know. I lived in a little place and went just off electric heat, and it was about $90 a month. So that was with the heater and the water heater and the stove and all that stuff. So there you go. This would be dollars per month to run a heater. Cool. Oh, and then because it was Mammoth, the cost was probably double. So yeah, that makes more sense. All right. So a fuse. A fuse, or a circuit breaker, is basically something within a circuit. Let's zoom in. It's something within a circuit that can open or close like a switch based on how much current is flowing through. So let's see what I say. Because power equals I squared R, as the current increases, the power dissipated in wires increases, meaning it heats up. So that when energy is dissipated in the wires, it turns into heat energy. So wires can melt or even catch on fire if too much current flows through them. Notice how the power depends on the square of the current, right? So doubling the current would quadruple the power. So a big wire like this has less resistance and a skinny wire has more resistance. Let's take a look at a little kind of circuit diagram of potentially what's going on in your house. So we have 120 volts, right? And all these appliances are wired in parallel. We're going to get to that. But what it means is that all of them draw off the same set of wires coming from the voltage source. So you could potentially be, here you are running your heater. Oh, it's that 180 watt, a 1800 watt, big boy. And then a hair dryer, and you're listening to music, and you have the light on in your room. So you may have had this experience where you run all these things and all of a sudden the lights go off and the heater stops working and everything. Because what happens is you blew a fuse. So this is designed to protect all the wiring inside your house from catching on fire. And we know, or the electricians know, okay, so the wiring, let's say, can handle a total of 20 amps. And that would be reasonable for some sort of big household wiring, you know, it could safely handle this. So you'd maybe put a 20 amp fuse or a 25 amp fuse in there. So if you're running all these things and you're drawing all of a sudden 30 amps, what happens is this is going to break or blow. So what do we know? Skinny wires would be appropriate for low current, and big wires would be appropriate for high current. And let's take a look at why. Okay, remember, if this has less resistance, if we look at this, right, if we have less resistance, it means, so this number decreases for the same amount of current, less power dissipated, so less power dissipated as heat. Meaning, if you have these two different wires, and they're both running the same current through them, this one's going to get hotter, and this one won't. So, bigger wires are safer in terms of them being resistant to catching your house on fire. So, let's take a look at the third page. This is just a couple images I'd like you to look at. So when we talk about wires, wires are measured kind of like shotguns, right? Some different gauges, and the smaller the number, the bigger the wire is. So once I installed a car stereo and I got an amp, and my subwoofer, and I was bumping the Snoop Dogg, and these big fat wires came with it. So these were the ones that went to the battery, right, and they came into the amp, and then the little speaker wires are still kind of skinny, and it was surprising. But this thing would get hot if you were really bumping those beats. The fuse box in your house is going to look something like this. All the wiring would probably be covered up by a panel, but it's these little things where the fuses don't actually break. What they do is it sort of flicks a switch if it's overloaded. So you can unplug the hairdryer and then turn it back on without having to replace something that has been damaged. In smaller appliances, you'll see a fuse and it'll look something like this. So, the current flows through here, and it's just it's basically a piece of wire where this is going to melt first before your wires catch on fire. So this would be a blown fuse, and you have to take this out and put a new one back in. The fuses in households are designed to just be a switch that flicks on and off.